Cool. All right. Welcome back, everybody. So I'm going to give an introduction to the Reuben Observatory Scheduler and our strategy and simulations. A lot of this is recycled content from the project and community workshop in August. So if you were there, this should look familiar. You can check your email for a while. Let's get right into it. There we go. All right. So first off, I just said this is a talk about the scheduler, and scheduler is actually a misnomer. We are actually using an artificial intelligence rather than a scheduler to make real-time decisions about what observations to attempt. So schedulers usually try to solve maximization problems. So for example, I've got Kepler on the right there. It was trying to maximize the probability of finding a planet in the habitable zone. That's one nice quantity that it could try to maximize when it was setting its observing strategy. Something like the Gemini telescopes, they're trying to maximize the happiness of their telescope allocation committee. For Reuben, we have 4 broad science goals, and so it's not clear how we could even cast this as an optimization problem. We don't even know the units that we would be optimizing. So we can't do a classical scheduler that like most astronomers are used to. So here is the scheduler in a schematic decision tree. We go through at any time, when we're simulating the telescope is open, we first ask, is there a deep drilling field we would like to observe? If there is, we send the deep drilling sequence to the queue. We refine the list a little bit. For example, we'll switch the order of filters to avoid excess filter changes and execute them. If there's no deep drilling field that currently wants to be observed, we try to observe a kind of contiguous blob on the sky. We call it the blob scheduler. This will execute if it's not twilight time and we have enough time to do a large blob, in which case we use a Markov decision process to select our contiguous area. And then again, we have some refining steps that we do once we make that list. And if it's twilight time or we don't have enough time, we go to observe a single pointing and use a similar Markov decision process, but now just pick one pointing. And my asterisk down at the bottom is we are actually running a second scheduler completely independently, which decides which filters should be loaded for the night. Reuben is a 6-filter survey, but we can only load 5 at a time in the camera. So currently there's an independent decision made on which 5 should be loaded for a given night. Our model observatory, we can give our model observatory commands like go observe this spot in the sky, and it will slew and simulate doing that. It has a full kinematic model of the telescope, the dome, the camera. We use a historical weather log to simulate weather downtime. We've set it so that we close if 30% or more of the sky is cloudy. So our weather downtime is very closely matches Gemini and SOAR, which are right next to us on the site. We have scheduled and unscheduled downtime. We have a historical seeing log, so we record the atmospheric seeing as if we were really running. We have a sky brightness model that we got from ESO, plus we used a twilight fit from an all-sky camera that was at the Reuben site. And here's a plot showing in blue kind of how much time we have on a given night of the year, and in orange the maximum that would be possible if there were never any clouds. And the vertical stripes are showing our scheduled downtime spots that we have every year. And so our model observatory gives to the scheduler kind of all the current conditions, says how long would it take to slew the positions, what's the current seeing look like, what's the current sky brightness look like, things like that. For our pointings, we use a sky tessellation that is based on a soccer ball tessellation, only we've got more hexagons. And so we say we can point to the center of any of these polygons. If we do that, this is what our sky coverage would look like. You can see most of the sky is covered just once. There are overlap regions between pointings and just a few triple spots. This tessellation, we spin it so the orientation is randomized each night. So there are no fixed fields for the wide area parts of the survey. So this is how we're going to accomplish our dithering and keep the co-added depths very smooth across the sky. We emphasize observing neighboring pointings. And so this is a zoom in on what a sky tessellation for the night might look like. You can see we've got these overlap regions. And so this is how we're going to meet one of the science requirement documents requirements of having fast revisits. So this area will be revisited on very short time scales, whereas the the purple area is getting observed once, and we'll kind of repeat those observations on 22-minute timescales. And so just to remind everyone, this is what the Reuben field of view looks like. Each little square here is a CCD. And so this inner circle is the science field of view, and that's what's here. So every now and then things get observed outside the science field of view and so on. All right, moving on. So here is an example single night that we've simulated of the observatory. And so we start in twilight, taking single observations. On the top is in RA Dec, on the bottom is Alt-Az with zenith at the center. And so you can see we're taking just individual observations scattered around that it wants to do. We move out of twilight, we go into the blob scheduler, and we're observing large contiguous blobs. We try to stay near the meridian. A deep drilling field executes, just one spot on the sky. It tracks it for about an hour. Then it goes back to doing blob observations and back to twilight mode. So this is kind of the progression of a single night of how we think things would go. And I'm showing all filters, but it is doing filter changes during these. All right, so the most important part, most of our observations are taken with this blob scheduler, and we're using the Markov decision process, which is popular in the robotics community. And it lets us really balance our different and often conflicting desires when we're observing. And when people hear Markov, they often think of Markov chains, and a Markov chain is actually a subset of the Markov decision process for when history doesn't matter. So a Markov chain is stateless. The Markov decision process retains the history of the system. So we're using all our previous observational knowledge when we make a decision with this. So here's our footprint in all 6 filters, U, G, R, I, Z, Y. And we're going to define these with HealPix maps at a resolution higher than the Reuben field of view. So we're tracking things at a higher resolution than our fields. So let me run the scheduler for a few days and then pause to look at how the Markov decision process works and the functions that are going into it. So first off is our survey footprint. We've input a footprint that we want. We say this is our final desired footprint, and the scheduler tracks where we have observed. And so I've reoriented this. So zenith is at the center and we're in Alt-Az coordinates. And so you can see negative areas are spots where the survey has observed a lot. Positive areas haven't been observed at all. And so this is kind of our map of how close we are to our ideal smooth survey coverage. Our next basis function is the 5 sigma limiting depth. We look at the difference between the current 5 sigma limiting depth across the sky and what we think the best possible 5 sigma depth would be. And so this map, the moon is down, so it just means the meridian is best for everything. And if we go to very high air mass, there comes to be a larger and larger penalty. And we do this in all 6 filters. So this will tell us to push to redder filters when the moon is up. Finally, we have a slew time map. It takes us about 2 minutes to slew around 180 degrees to the other side of the sky. So observing near where we're pointing is rewarded. Observing the other side of the sky is penalized. And this is kind of my image of what the Markov decision process is doing. Our free parameters for the scheduler are how much weight we put on these 3 different things. And what we found is if we put too much weight on any of them, it shoots the other 2. If we only care about observing a smooth footprint, the scheduler loves to flop over to very high air mass and just keep things as smooth as possible. And so that destroys our image depth. If we only care about slew time, then we won't be able to get a smooth footprint. There will be spots that get left behind. And so we try to balance these 3 parameters to get the final scheduler. A couple other things that are in there. We have some simple masks. We mask around the moon. We mask around zenith because we can't track through zenith, so we mask that out. And we put a little extra shadow on zenith because we want to take observations in pairs. So we don't want to start something because then it will track into zenith and we won't be able to complete the pair. There's a basis function that also rewards staying in the same filter because the camera takes 2 minutes to change filters. So there's a slight reward there. And so if we sum all of that together, this is what the Markov decision process reward function looks like during the middle of one of our simulations. And so what you can see is at high air mass, an area that has already been observed a lot is negative. And at low air mass, a region of the sky that hasn't been observed is quite positive. And so this reward function will select this area to tessellate and observe. So, and by design, our reward function is fairly smooth and slowly changing over time. So we're not too worried about, like, if we set and decide to observe for 22 minutes, the reward function won't change radically during that time. So we can go ahead and plan a little bit into the future with that reward function. And as I said before, our tessellation of the sky gets randomized each night. And so we map these heel pixels to actual pointings on the sky. And so that was this part of our decision process that I just ran through, is using that Markov decision process to select the contiguous region. Once we select it, we go and do some refining. Here's what the refining looks like. This is just the list of pointings in RA and DEC, and I've color-coded them by how much reward there is. If we just blindly observed them, we'd make a path on the sky like this. So we pass it to a traveling salesman problem solver to get an optimal path, so that, again, we're usually observing neighboring fields. And then we'll refine that list further to say swap filters and repeat the path so that we get observations in pairs. And so the end result, after simulating for 10 years, looks like this. Here is in RA DEC space our final footprint. It looks like the footprint we input that we wanted it, so it did indeed stay smooth. You can see some of the deep drilling fields. There. We've got the 5 deep drilling fields. In Alt-Az space, you can see this is a log stretch. So we really do hug the meridian for the most part. We are not chasing things to high air mass very often, just once or twice. And then in the lower right here, I'm color coding time based on what filter is loaded in the telescope. These white bands are weather downtime and scheduled downtime. And this dark line at the bottom is phase of the moon. And so you can see when the moon gets full, we go to the redder Z and Y filters. And then when it's new moon, we're in the bluer filters. So everything is behaving pretty much as we expect. And one of the things we often get asked is, what can we change? What's easy to simulate? What's hard to simulate? And so I like to point out that we have this decision tree. It's modular. We can pop in new blue boxes if we want to. The Markov decision process is modular. So we had our 3 main basis functions, but we can add more. We can put different weights on them and vary them. So that's very easy. And then these detailers that refine the list are modular. So we can really do anything we want in this process, and it's very easy to swap things in and out. So what can be hard? If you want to observe a very specific sequence, say, night 1, you want to observe in G, and then night 2, you want to observe it twice in R, and then night 3 in I, this is hard to do because, we don't have fixed fields. We're randomizing our tessellation every night. So, and we also need to know, what do we do when weather interrupts this sequence? What do we do when the moon comes in and interrupts this sequence? So this is really hard for us to encode, especially in our current format. The other thing that's difficult is if you say, oh, I see these observations here, I want to move them to this other block of time. And that can be hard because we have to go back through the decision process and figure out, why did it decide to put that block there, and how do we undo that? So that can be hard to disentangle. And so this just kind of shows that usually when you're planning observations, you do it in a block schedule. You have a list of fields, you have a list of times, and you pick one at each time block. And we're not doing this because we have 5,000 fields. We're doing 2 million observations in 6 filters. So we would need a 10 to the 10 element block scheduler, which gets to be a little cumbersome, especially if we need to do things dynamically. If the weather closes us for an hour, re-optimizing a 10 to 10 element block scheduler is probably not going to be fast enough. So it's not impossible, but there's nothing off the shelf that can deal with the raw Reuben scale scheduling problem. So that's why we're going more with a decision process and a decision tree than this typical block that you'd be used to. But I will note the deep drilling fields are just 10 to the 5 element grid. So we're looking at doing the deep drilling field scheduling independently and just having that pre-optimized on a grid, and then doing the rest of the survey with the decision process. Okay, and just another example, I want fields to be observed once every 3 days. That's hard, but that's difficult to encode in our current system. But if you say, I want to suppress the reward given to areas that have been observed in the last 48 hours and increase the reward on areas that haven't been observed for 72 hours, that's very easy for us to do. And so this is probably the behavior you'll want, but now we're doing it not with fixed fields and over large contiguous areas of sky. So oftentimes it's just a matter of rewording what you want it to do to get it into our process. So we often get observed, can you observe like X? And so the answer is almost always probably, but we might need to think about where the best spot in this decision flow is to insert, your particular observational desires. So my conclusion so far, we have an artificial intelligence that, as we'll see shortly, does a pretty good job of observing. So I will pause there for questions and things. We're going fast.
Hi, this is Rafaela speaking. I have a question. How do you envision TOOs to be incorporated in the scheme?
An excellent question. So we simulated TOOs about 2 years ago. We injected basically a gravitational wave follow-up events. I think that's the only TOOs that we're considering that Reuben would be used for. And so there are a couple ways we could imagine TOOs. It could be we just interrupt and manually chase them, or we could have something in our decision tree, something at the top of our decision tree that says, if a TOO comes in and we think, you give it an RA and deck, it will just automatically go and observe that portion of the sky. And so that's what we simulated before. And it works pretty well, especially if we say, only try to chase TOOs that maybe overlap with the main survey, because then those observations can count towards the science requirement document requirements. And so, yeah, we can have TOOs in here. We've done simulations. If the TOO community wants to come up with some more realistic TOOs, we can keep working on that.
Thank you.
All right. Looks like there was some stuff in the chat. Yeah, go ahead.
Another question. So I know you guys have thought about this, but what about how does the satellite mitigation work in this scheduling?
Indeed. So I knew this would come up. I had the slide. So yes, lots of people have been concerned about the Starlink mega constellations of satellites going up and what that will mean for our observing strategy. So I think, yes, there will absolutely be some satellite streaks in Reuben images. There would have been streaks even before Starlink. One of the nice things is Starlink is in low Earth orbit. So those satellites, while they're very bright, they're moving fast enough that they won't saturate the chip. So we lose pixels, but we don't lose entire CCDs if we get a streak. And so here's some of the simulations we did looking at, this is at Reuben Observatory, kind of if there's a 12,000 satellite constellation running around in 10 minutes, this is what the streaks on the sky look like. And if there's 50,000 satellites, it starts to look like this. And one of the things we found is we really can't dodge them, even though we know the orbits of the satellites and where they're going to be. If we try to start dodging around them, we're going to be slewing so much that our efficiency drops more than just losing the pixels to the streaks. But we can fold things in, like we could say, well, this area of the sky has many fewer satellites going through it, so let's just observe here, and we'll have many fewer streaks than if we we're chasing something to higher air mass over here, where every image would have multiple streaks. So there's some ways to, it's very easy to decrease the number of streaks we'll see, but there are definitely going to be some, and please don't make me try to dodge all of them, because that's hard and inefficient. Will, I see Will.
Peter, at what level does the distinction between the main survey and mini surveys make a difference? Is there any, because I imagine those weighting functions might be different for the mini surveys compared to the main survey. Are there sort of...
Right, you'd think so, but actually it depends on the mini survey. So the deep drilling fields are kind of broken off completely independently. We just basically give each deep drilling field a 1% cap and say, you can execute, but if you're over 1% of the total visits, you can't. And so that caps them and they run independently. But for the South Celestial Pole, the North Ecliptic Spur, they're being treated just like wide, fast, deep. We're just giving them a lower target on the footprint. So it's kind of a uniform survey, and that helps the scheduler, because then the scheduler can, either just observe wide, fast, deep, or observe a region that is both wide, fast, deep and the NES contiguously, and it doesn't have to decide one or the other. It can do both. Yeah, so they are not broken out. We can break them out, but currently we haven't needed to.
Thank you.
Peter, can I? Oh, sorry. Was there a follow-up?
No, just a very quick question on this slide. The white areas are due to bad weather, or?
Yes, these white stripes are bad weather and the
scheduled
downtime.
So I was going to bring up one of the questions from the Zoom chat. I've answered some of them in there, but there was a question about early science, and is there a plan to visit specific fields more frequently than the first half year or your first 1 or 2 years this is for a particular early science goal?
Right. So far, we haven't simulated a lot of different strategies for the first year. One of the constraints we're under is we almost always observe the first year and the last year very uniformly, so that we get proper motions down to the required precisions. We need that 10-year baseline to do proper motions. So pretty much we're going to try to cover the whole sky, evenly in the first year and the last year. Yeah.
I'm also going to add, this is a good question that the SCOC are planning to address later in their process. That what early science variations on the overall survey strategy should we do?
Can I ask a follow-up question to what you just said, Peter? When you say the first year and the last year will always be done uniformly for proper motion precision, is that true for every mini survey as well, or is that separate?
Currently, it's everything. If we want to break the footprints out and do them differently, we could. And there's definitely been a discussion of doing funny things with the deep drilling fields. For example, like we could we could only do a deep drilling field in years 4, 5, and 6, and just have that piled up there, and then not do extra deep drilling field observations in some other years.
But it's worth noting that when you say uniformly, you don't mean uniformly across the sky. You mean that relative to their overall fraction of visits. That you do. There was a comment in Slack or in Zoom that the bulging galactic, the galactic plane area gets fewer visits, and so they get fewer visits in year 1 and 10, which is true because they get fewer visits overall. But they are, you could think of how the initial survey strategy is that in year 1 and 10 we try to take what would have been the 1/10 of the visits for the whole survey and do those visits in year 1 and 10. It may be that the SCOC says, hey, early templates are really important, so we should make sure that we cover the sky with a certain number of visits in each filter. That fits fairly well into this general plan, and they may have other suggestions later, but the idea. Okay, Lucienne. So I have heard people say SCOC, and I have heard people say SCOC. So at some point, yeah, sure. If the committee would like to be called the SCOC, that's fine with me. So the SCOC will address the question of early science priorities after some comments on the overall survey strategy. Things like determining the footprint, for example.
Oh, and I see Rachel asks, can we project in advance what we expect to observe? And so we're currently working on how exactly we're going to implement this in operations, but I think currently our plan is at the start of the night, we will simulate the night, and that will be our projected night. And if weather closures happen or other things get us off that script, we'll regenerate it. But our current hope is that yes, at the start of the night, we will have a rough plan of what we're doing for that night. I don't know if we can do multiple nights, but we can definitely think about it.
Yes, the information will be shared in real time with the community. There is a requirement on the scheduler that we publish. I think it's an hour and ahead, the most likely schedule, and the goal is to make that as long as possible.
There are questions about winds, and so currently we're not simulating winds, but with the Markov decision process, we can just feed in a map that says this area of the sky is currently blocked due to winds, so you can't observe there and go do something else. So we definitely have the capability to dodge the wind, but yeah, we're currently not using forecast that much. Also, we currently don't have by default a requirement for image quality. So we're taking so many observations that we tend to get good image quality across the sky regardless, but we're not using the forecast for, say, image quality to say like, oh, it's a good seeing night, we should be in G, or it's a bad seeing night, we should go redder. Where there's potential for that, but we haven't had a science driver to make us do it yet.
On Slack, there's a question about the cutout around bright planets and which bright planets are we dodging and how big is the cutout?
An excellent question. I didn't include that on my mask map. I think we're currently masking Venus, Mars, and Jupiter. We masked those. I tried masking Saturn, but Saturn moves so slowly it makes things ugly. And the mask size is just the field of view, so just 3.5 degrees around the planets, and we can take those on or off as if people want. Oh, yeah. And there's a question: is it known which filters will produce the best images? Probably, but not by me. Yeah, I think G and R are probably going to be the highest image. And Dave asks, what's the mask size around the moon? The default is 30 degrees around the moon. And there have been questions of whether we need to bother with that or not, because the 5 sigma depth basis function would avoid it anyway. And that would let us get closer in red filters, and we're already dodging in blue. Will the data be sorted by image quality so best images can be retrieved later?
Do you want me to make a comment?
Sure.
Actually, if we have Colin here, Colin or Melissa would be great people to answer this.
Or perhaps I was meaning to say flagged in terms of image quality.
So the metadata for every image will be available. So there will be measurements of like estimates of the 5 sigma depth and in the delivered seeing. And so you could go through the list of images for a particular pointing and find which ones those would be the best ones for your purposes.
Right. And there's a question of how fast can filters be switched. It takes 2 minutes. So we're not going to do hundreds of filter switches during the night. One of the early decisions are the very early simulations. We tended to get pairs of observations in the same filter. And so we tended to just have, a single filter per night. And there's been a pretty large push by the transient community to say, like, we really need color information on our alerts. And so so we're running slightly less efficiently. I think it's about a 4% hit. And so you can see in this color coding where it goes, green, blue, green, blue, green, blue, it's doing, GNR pairs throughout the night. And so we do switch filters about every 44 minutes, and our upcoming release will have variations on that, where we swap the filters either more rapidly or less rapidly. So yeah, there's that. Are we worried about?
Let me just interrupt you for a second. It would be easier on us if the new questions were coming on Slack rather than here. We have to keep them. We have to move them from here to there for archiving. So if you have another question, just type it directly to Slack, not here. Thanks.
So yeah, another question about filter changing. I don't think we're close to our filter swap limit. And if we break the filter changer, we can probably make a new one.
No,
there are constraints. It's about 30,000 changes per filter.
Yeah.
There are details about it in solicitation for white papers as of 2 years ago. It's easy to find the document.
All right.
Lynn, how shall we ensure that we have all the questions from Zoom chat captured on Slack? Should I make a copy of everything?
Yeah, why don't you do that? I'm working on putting the earlier questions through. The later questions I don't have, so yeah, that would be good.
Yeah, so for future questions, please put them on Slack. The Zoom chat is if you just want to interrupt the speaker immediately and ask something that is not, that cannot wait to the end of the talk. But for these substantial technical questions for after the talk, let's use Slack because it will be archived and then we have everything in one place. So are we done with all the questions that we have on chat now? Peter, that's basically a question for you.
It looks like it.
Okay.
I think so.
So we are ready to go with the second slide deck now.
All right, let's go. Let me go ahead and start up slide deck number 2.
So again, if you want to ask Peter something during his talk, something to clarify that cannot wait to the end, please do ask in Zoom chat. But for substantial technical questions, let's use Slack.
Okay, back-to-back talks, here we go. Okay, so we've discussed how the scheduler works, and now we'll talk about kind of the variations on those themes that we've run. And this is kind of a recap of that large document that Lynn and I put out, talking about all the things. So we talked about this briefly at GatherTown, but kind of how we decide what to run. The Science Advisory Committee gave us a list based on those 40 plus submitted white papers. And basically, if someone has come up with a good idea that's easy to run, we usually just run it. If someone comes up with an idea that's obviously a good idea, we usually just run it. And so we encourage people to go to community.lsst.org. So if you ever have thoughts about how you think Reuben should observe, just put it up there and we'll check and see if we can run it for you. So our baseline survey that we've already seen, for those who are new, this strip is the Galactic Plane, the South Celestial Pole at the bottom, the North Ecliptic Spur up here. The big yellow region is the wide, fast, deep, and we have our deep drilling fields throughout there. And this is kind of the footprint that's just been passed down for a decade plus now. The idea is the science requirement document says we need 18,000 square degrees, observed 825 times. So that's the wide, fast, deep region. The North Ecliptic Spur is added on so that we ensure we get solar system objects. The galactic plane is crowded and dusty, so we observe it a little less than wide, fast, deep, just because we won't get as much signal. The south celestial pole is at high air mass, so we also don't spend as much time there because we won't get as much signal. And for the deep drilling fields, 4 of them have been announced so that folks could go get precursor data from space observatories and things like that. And the 5th field will probably be the Euclid double field down here. So as we talked about before, we try to observe where there's the least depth penalty. So that means on the meridian, we avoid zenith because we can't track through it. And we've seen this plot before. We're observing in pairs. We usually do neighboring filters, U plus G. We can also do U plus R, but G plus R plus I plus Z, Z plus Y, or Y plus Y. And we space those 22 minutes apart. That's so that we can identify objects that have moved and also get any color information on transients. And we're trying to do our redder filters in bright time and twilight time. We try to observe neighboring fields. We talked about that. All right, let's go to that's the baseline. Let's go on to the experiments. So one of the things we've talked about a lot is rolling cadence. And this is an example of what we mean by rolling cadence. Rather than uniform coverage every year, we emphasize some region of the wide, fast, deep area and de-emphasize others. And so this is 3 different iterations of rolling cadence, where instead of looking at the full 10 years, I'm looking at year, I think, 3.5 to 4.5. And so what you can see is instead of uniform coverage, we have some areas of the sky that are observed many more times than other regions. And then in other years, this will flip so that after 10 years, it will look just as uniform. Static science will get the exact same depth. However, for these, we've got more highly sampled light curves for half the year. So as we talked about before, years 1 and 10 are always observed without rolling. So 1/10 of the total observations are taken in year 1 and 1/10 in year 10 to meet our proper motion requirements. So typically years 0 to 1.5, we run uniform. Then 1.5 to 7.5, we have 6 full seasons of rolling cadence. And then 7.5 to 10, we're back to uniform. And this is kind of a result of when we turn on the telescope, much of the sky is already halfway through or more of its observing season. So this is why we get this extra 1.5 years in here. So it's a little unfortunate because it means we have 7 potential years for rolling, but 7 is a prime number. So in effect, we have 6 seasons that we can do rolling cadence if we want to. And we have run a large number of simulations doing this rolling so that folks can see how their light curves look, and if this is a better strategy than just going uniform all 10 years. All right. So here's another example of rolling where this is my top column here is after 10 years, and then the bottom is our baseline year 3.5 to 4.5. It's nice and uniform. And in this rolling one, we've gone ahead and made 4 stripes. And I like this particular strategy of doing half the sky because here we always have a northern part of the survey with rolling on, so telescopes in the north can still pick up on the alert stream. Whereas if we go back, if we have something like this where we divide the sky purely in half, rolling is on and almost all of our alerts are coming in the southern half of the sky, so any telescope in the north is going to be cut off from almost the entire alert stream. So if we adopt rolling, I'm pushing this kind of style of rolling so that everybody can follow up and we don't completely overwhelm even more than planned the southern telescopes for follow-ups on transients. All right, we're blitzing through a lot of experiments here. One experiment we also did was varying how often the U-band is loaded into the camera. This is mainly driven by tidal disruption event identification. And so just increasing the amount of time that U-band is in the telescope and how much U-band we're executing is one of our simulation sets. We also varied how much time we give to the wide, fast, deep from 65% of the total time up to 99% of the time. And so you can just see up here, it's a very starved wide, fast, deep that probably doesn't meet the SRD requirements, and just slowly cranking up to where we're, very much starving the North Ecliptic Spur and the Galactic Plane, and almost all the time is spent on the wide, fast, deep region, getting up kind of over 1,000 visits per over the 10 years rather than the usual 825. So that's an observing set. The Science Advisory Committee, we got a lot of white papers on the galactic bulge, and so we did a set of simulations varying how we cover the bulge. We cover the bulge as part of wide, fast, deep, or as part of wide, fast, deep plus even more I-band coverage. So we have a variety of ways we've covered the galactic bulge. What else do we have? Footprints. Swapping in footprints is very easy. So pretty much anytime someone says, I'd like a Reuben footprint that changes this way, we just run it because it's easy to drop in. And so here's a huge variety of footprints that we've run. Some of them, just completely cutting out dusty regions of the sky. Some of them turning the galactic plane into wide, fast, deep, adding the Magellanic Clouds, covering a northern stripe so that we have template coverage if we want to chase TOOs to the far north. So pretty much any footprint that's been proposed, we've run. The deep drilling fields. So here I'm plotting for a single spot on the sky. It's usually RA0 dec -20, and I'm just color coded by filter the 5 sigma depth at that point over all 10 years. And so these are 4 different deep drilling field strategies that we've tested, kind of our baseline, a strategy put in by the AGN collaboration, where it really hammered it that one year, a strategy where we try to observe the deep drilling field almost daily, and so you can see it's really executing a little bit every day, and a strategy from the Dark Energy Science collaboration where we're spacing things out a little differently. We still haven't really converged on a deep drilling field strategy yet, so we're hoping to break that scheduling out and get it really optimized soon. And we're definitely looking for better ways to analyze the deep drilling fields, because they are unique enough compared to the rest of the survey that they need a little special care. Another experiment we ran, there was a proposal to use Twilight Time to take very short exposures, kind of at high air mass, to look for near Earth objects. And so this is an example where I've just broken off the rest of the survey looks normal, but these extra observations were done in Twilight Time, or these alternate observations were done in Twilight Time to search for NEOs in this kind of footprint. All right, variable exposure time. There was by default, we're taking 2 15-second snaps at every position, either 2 15 seconds or 1 30-second. And so there was a proposal that said, based on the current observing conditions, either extend or contract that exposure time so that images have more uniform single depths. And so you can see, again, one spot in the sky, our baseline versus if we vary the exposure time. And you can see, especially in wideband, because we take wideband in bright time and twilight, it goes from a scatter of 0.3 megs down to 0.2 megs. And so this is a little more uniform. I wish someone would give me an excuse to run more of these, because it sounds like a good idea, but we don't really have any science driver telling us that this is in fact a better way to run the telescope. What else do we have? We have observations intentionally taken at high air mass in the bluer filters to correct for differential chromatic refraction. And so here on our alt-as plot, you can see there's now this band at high air mass that we're taking a few images at high air mass intentionally. And there's a paper in prep that we'll probably hear about tomorrow during a lightning talk about how we can indeed measure the DCR effect much better if we take a few observations intentionally at high air mass, and we can see, is this just, and we can compare it with other science cases to say, is the lost depth worth the gain for this science? And so this is where I ran out of energy for pulling plots, and just will list some of the other experiments we've run. We've tried taking all filters in bright time instead of running to the red. This was motivated by some transients, especially supernovae, wanting that blue filter information and not having very long gaps between G-band observations. We've tried taking pairs only on the ecliptic. We've tried rotating the camera so that diffraction spikes stay aligned with chip rows and columns. And we've talked before about the target of opportunity follow-ups that we've simulated. All right. One thing from our report is in our version 1.6, we kind of came up with this potential new parameterization for the footprint instead of our old baseline. And so it should look pretty familiar. We've still got wide, fast, deep. We've still got the north ecliptic spur, but now instead of just the galactic plane here, we've taken the full dust extinction affected area of the disk and decreased the emphasis there, but added the bulge and kind of a bridge here to the wide, fast, deep. So the bulge is treated as part of the wide, fast, deep. We also add the LMC and SMC as part of the wide, fast, deep area, and the stripe for TOOs. One of the problems with this is doing this, you'll notice this right ascension has lots of deep drilling fields, lots of wide, fast, deep, and the NES. So we get oversubscribed pretty harshly in this region. So it's going to be difficult we almost certainly have to cut some of this northern region out of wide, fast, deep if we're going to keep this reasonably subscribed. And the Dark Energy Science Collaboration has been pushing very hard to get 18,000 square degrees that is low extinction, but just because of the shape of the sky and the seasons, it's going to be really hard to do that. We almost certainly need some of the wide, fast, deep to go through the Milky Way plane, definitely on the anti-bulge side and probably on the bulge side as well. So some upcoming experiments that we have, we've put a custom dithering strategy in for the Euclid field, so that in red here is the Euclid footprint, and here's one of our simulations where we dither specifically to try to fill that better than just random dithering. We have new rolling cadences. Some of our old rolling cadences had bugs, and we've fixed those bugs, so we've got even more rolling now. Variable pairing times, so we've always run 22 minutes, but we're trying different ones. We'll try taking pairs in Twilight. If you remember, right now we're just taking single observations, but we can do pairs in Twilight. Longer U-band exposures, going up to 40, 50, or 60 seconds, so that our U-band observations are not read limited. G-band observations in bright time still. We're looking to improve that NEO Twilight survey. There were some things that could be better about that. And we've talked about doing the DDF independently so that they can be optimized and their strategy set independently. All right, conclusions. We've varied the survey strategy a lot, and kind of the most pressing questions that we still have are, what should we use for the survey footprint? Should we do rolling or not? And the details of the deep drilling fields. All right, I'll stop there for questions.
Thank you, Peter. Well, it looks like most of questions are on Slack.
Yes, here they all moved to Slack, so that's great.
To help Peter with these questions.
Yeah, a lot of them were somewhat addressed, but here's some that I think we can bring up here. First of all, the galactic plane definition. I think that most people generally agree that the northern little bit of the galactic plane is not necessarily to conserve, and we should trim it out. I think that's fine. It's a small area, and we generally have compared to a baseline that has it, but yeah, that sounds good to go forward. The other one that I think maybe we might be good to discuss a little bit more is Fed asked, in the blobs, the filters are consecutive. So we pair G with R, for example, and R with I. And she points out for identifying transients and for classifying variables, I think that's the motivation. Having those filters be more separated in wavelength would give you more leverage on the SED to extract useful colors. So why do we pair them in consecutive filters, and could we could we simulate them with wider variations? So I'll leave that if you can.
I got lost there, sorry.
Oh, sorry. So in our simulations in the blobs, the pairs are G minus R and R minus I typically. And so consecutive filters. Why don't we do non-consecutive filters?
Oh, it's a good question. We could if we wanted to. If so, that's kind of just been a default. And a lot of it's driven because we're picking filters based on image quality and sky brightness. You know, there's not much time where it makes sense to do, you know, G plus Y, but we could.
Yeah, I would note that doing them in consecutive filters is nice because it puts them in similar alignment with the lunar cycle. So G and R would have much more similar lunar requirements and M5 requirements. So you may want to pick those carefully. The other thing is that for solar system completeness, having filters which are similar is better. Having filters which are the same is best, but the hit on transients and variables by having different filters is much larger than the gain for the solar system by having the same filters. So having different filters is useful. Having something like R paired with Z would be pretty bad for the solar system because that would make that pair not a good pair because Z starts to be pretty useless. So again, it will end up being a trade. I think it's something we can simulate and have a look at. It may end up being something that we want to do a more complicated simulation instead of just splitting them into wider sets, trying to do something where you sometimes have the same pair, sometimes have different pairs.
Okay, next.
Yeah, sorry. So there was a question about, paged up too far. I think so there's experiments doing alternative strategies for the footprint cadence and filter selection specifically to the field that are a wider variation than we currently have. And I think this is coming in large part from the transient variables science collaboration. So I think this is something that we should probably talk about offline. Some of it we can probably do straight ahead. Some of it might need to go in the cadence notes. I think we can look at that. And then there were a lot of questions about rolling cadence.
Yeah.
So
rolling cadence, one question here is, how do we define the frequency in rolling cadence? And that's actually one of the things we varied in the experiment. So here I'm just showing, I think this is an 80% rolling cadence where we say for the regions that are not emphasized, we're going to cover at 20%, and the regions that are emphasized are 180%. And we varied that fraction. So not only the number of stripes, but how strong that rolling fraction is as well. So that's one of the things we varied. And someone else Massimo is asking, the effectiveness of rolling cadence should be demonstrated on actual data, and absolutely. And so we'll get into, we have some metrics to look at variables and transients. So we inject type 1a supernova light curves and see how well they're recovered. We inject tidal disruption events and see how well they're recovered. So, but we could always use more. So there's definitely some metrics that touch directly on rolling cadence, but we're always looking for more. Will asks, is there any plans for a short exposure survey? And that's one that I didn't mention, but we have simulated that, I think, looking at 1 second and 5 second exposures, where we simply ran it as we went across the sky. If we got to a spot that hadn't been observed with a short exposure, we just took one. So we can do it. It'd be good if someone gave us a good science motivation and shit. So after doing that, it's a very small penalty on the rest of the survey, but I don't think we have a strong driver. Will.
I think there was a 2018 Cadence white paper that recommended a short exposure survey. I believe that was led by John Gizis. And I know that Chris Stubbs had talked about this a few years ago. So is it the case that a cadence note to sort of reinforce that science justification would be helpful?
It would be fantastic, especially since we ran the simulations. If someone took that simulation and said, "Look here, I can do science that I can't do in the baseline simulation," that's a perfect Cadence note.
Okay, thank you.
And Eric's asking why start rolling after 1.5 years instead of 2 years, and it's because we want the rolling to be full season length. And so if we start at 2 years, then half the sky will be through its observing season. So you'll get broken coverage on your light curves. But yes, it will make the Y2 data release non-uniform. So that means that there will be some uniform data. Well, maybe there won't be uniform data releases until the end of rolling, but we should check that. And Franz is saying it would be very helpful if science collaborations could simply provide light curves rather than code it up in math to test this. And absolutely true. And we have examples. So I think the light curves we've collected have been collected from the community, and we have pretty easy to follow math templates where we can just convert. So if you have a population of light curves that you'd like to test and see how they perform, we can modify what we have very, very quickly to do that. Question on, can TOOs use longer exposures? That's an interesting question, because if it goes longer, it could still be used for the science requirements document, but it would be a less efficient way to be it, so that it wouldn't count as much towards the main survey. But I imagine we could do TOO observations longer. I'm not sure there'd be an advantage over just, say, taking a series of 30-second exposures, take 5 30-second exposures instead of something else. But the other thing for the TOOs that we haven't talked about is that there are chip gaps and raft gaps. So if you're hunting for a target of opportunity, you'll probably want to dither to fill in those gaps in case your transient fell in a gap. And so again, the 30-second exposures might make the most sense, and then do a raster pattern to fill in the gaps.
It's also worth noting that with a 30-second exposure, LSST saturates, or Reuben Observatory saturates at about a 16th magnitude.
Mm-hmm.
So 180-second exposure, there will be a lot of saturated things.
Okay. Any more questions?
I haven't seen any more. There was some discussion on other simulations that we could improve, and I think those are probably best handled offline, and we can go back and talk about that with the solar system collaboration for the Twilight survey, and with the TBS for these other footprints that they would like to have a look at.
It looks like we ran out of questions. So the rest of this session is supposed to happen on Gather Town again, with the same idea as earlier, that you would talk to your SCOC or SCOC liaisons, and then they'll get back to us with comments that were made during the session. So after breakout discussion, we will be done for today. So on Zoom, we will reconvene tomorrow morning, evening, depending on your time zone, but same time as today, 9 a.m. Pacific time. And then Lynn will show how to analyze in more detail these simulations that Peter just talked about. So let's now all move to Gather Town and reconvene on Zoom tomorrow. Thanks a lot for dialing in today. There are over 100 people. This is fantastic, and I hope we'll retain this enthusiasm for the next few months when we need to quantitatively analyze all these simulations, as we will discuss tomorrow. Thanks, and see you in Gather Town.
Yeah, and just a note on Gather Town, all the science collaboration areas are now private spaces where you talk to the people inside that space and nobody else, and hopefully that will deal with some of the oddities around proximity.